Hi, my name is Guy Davidson, and today I'll talk to you about some work I've been doing with Brendan Lake at NYU on investigating simple object representations for deep reinforcement learning. Our motivation comes from the fact that while deep learning has been incredibly successful in tasks such as vision, language, and game playing, in the field of deep reinforcement learning, this success has come at the cost of great sample inefficiency and a rather weak capacity to generalize. A few years ago, Brendan and colleagues outlined some ideas about how we might bridge the gap between today's machine learning approaches and more human-like learning, and we're focusing on object representations as part of the core knowledge that people seem to have access to from infancy, as outlined by Liz Spelke and colleagues. Why do we think object representations are important? They're one of the most well-studied core knowledge systems. They're lacking from most model-free deep reinforcement learning methods. We think they might aid in generalizing systematically, and we could simply approximate them in Atari Frostbite. Atari Frostbite is the game you see here on the right, where the agent must build an igloo in the upper right-hand side by jumping between ice floes, while avoiding malicious animals such as the fish and crabs, eating fish for bonus points, and doing all of that before time runs out and receiving a bonus for finishing a level. We approximate object representations by computing object masks, identifying each object by its color and location, and we pass these binary masks to the model alongside the pixels. We have three experimental conditions. Pixels is a standard rainbow model by Hessel and colleagues, at the time the state-of-the-art in model-free deep reinforcement learning. In Pixels and Objects, we also pass all of the object masks you saw before, each in a separate channel alongside the pixels. Finally, in the condition we call Group, we combine all of the objects to a single channel, as you see here on the right, in order to ablate the importance of separating to separate channels. Results. So first we find that object representations do in fact aid learning. By about a week's worth of human learning time, we find that the model that receives the separate objects performs the best, afterwards the model that is grouped, and finally the model that sees only the pixels. We also find that earlier on, the more abstract representations of the grouped object are actually better than both the pixels alone as well as the more complicated semantic representations of separate objects. We also wanted to evaluate how our object representations might help the models generalize to novel situations. To do that, we take a saved observations and add and remove objects, changing the masks to match. We record the state value the models in each condition assigned to these novel states, and we plot the distribution of state values for each condition. In our first novel scenario, we surround the agent as though it was a bonus level. If we surround the agent with fish, we see that the pixels and objects model, which sees each object mass separately, indeed increases its state value prediction, as we might expect, while the pixels only model drops it, and the grouped model remains at around the same level. If instead we surround the agent with crabs, which would kill the agent upon contact, we see that the pixels and objects models appropriately lowers its state value prediction, while the other two models don't seem particularly fussed about this change. Now, if we surround the agent with aliens from Space Invaders, which it had never seen, and mark them as though they were good, that is, like fish, edible for bonus points, for the pixels and objects model, it indeed responds positively to them again, while the other two models again do not change their predictions all that much. And finally, if instead we mark these aliens as bad, that is, as the same category as the dangerous crabs, we find that again the pixels and objects models drops its prediction, while the other two models understandably do not change their prediction, as for them the situation does not change. We now examine what happens when we strand the agent on a single ice floe surrounded by crabs, with no escape route to the safety of the igloo. Regardless of whether or not the additional ice floes we add offer an escape route to safety, or are simply distractors, we find that the models don't respond significantly differently to any of these changes, and don't seem to recognize that only the escape route offers a path out. This seems to tell us that these object representations do aid generalization, but only under some conditions, and we're trying to think about how we can better understand these results, and what are the limits to the systematicity they confer. To summarize, we found that simple object representations do aid model-free deep reinforcement learning, and that particularly our more abstract grouped objects seem to help early, while the more semantically specialized representations seem to help later in learning. And we're now wondering what other cognitive components are necessary for human-like reinforcement learning. Particularly, we hope to spend some time thinking about more cognitively plausible object representations, as well as learning policies directly from objects, and whether or not such object-oriented policies can be simpler, more interpretable, and more robust and amenable to generalization. Thank you.